Newtonian mechanics doesn't always work. I want you to imagine a boat. The boat is traveling at a velocity. There is someone on top of that boat who throws a ball at a velocity. Newtonian mechanics is what we would use to find out the velocity of that ball that is traveling. It's what we use to understand the universe and how things move and whatnot. However, if you take that same boat and you make it so that its velocity is just underneath the speed of light, and you got that same person to throw a ball somehow, if you were to use Newtonian mechanics, it would suggest to you that that ball would be traveling faster than the speed of light. However, we know that the speed of light is a speed limit that cannot be exceeded. The speed of light is a constant, and so Newtonian mechanics breaks down in the relativistic frame. Einstein then proposes special relativity, which is basically where we use a Poincare transform to govern we use a Poincare transform to govern a situation like this, and we see that the Poincare transforms retains the speed of light, so its mathematics doesn't allow for things to travel faster than the speed of light, and it also shows that in the non-relativistic frame, those Poincare transforms, I'm not sure if I'm saying them right, reduces to Newtonian mechanics. Special relativity is a special case, however, because it does not include gravity. Now, in 1907, Einstein released the equivalence principle, and the equivalence principle is what was the missing link between special relativity and general relativity. So imagine you are in an elevator and you feel a force coming from beneath your feet. The principle is that you cannot tell whether that force is due to gravity or due to acceleration. So the equivalence principle states that what if gravity, there is no difference between gravity and acceleration. Then you might ask, what's that acceleration being caused by? If it's not gravity and it is acceleration, then what is it caused by? And Einstein's answer to that was the source of gravity is the free falling due to the curvature of space. And if space-time curves due to mass, then we have to think about the universe in a much different way, right? There's all these different masses in the universes, and if each one of them is curving space-time in a certain way, then the shape of the universe is going to be different. So it's kind of like a rocky terrain in a mountain, right? So that's the kind of manifold, the space-time manifold that we're dealing with, and therefore, now that we have this kind of like updated image of the universe, we're able to shift our thinking. We're able to stop understanding gravity as a force of attraction between two masses, and we just understand it as a response to the curvature of space-time. So if space-time is curved, then we need to change our thinking. So we need to introduce two things. One is called a geodesic and one is called a tensor, and they will help us model that curved space-time universe and able to move forward towards general relativity. So if you think about space-time as a rocky terrain, we can think about a geodesics as the highway, the road that is traveling in between those mountains. A geodesic is the shortest path possible in the 4D space-time manifold. The equation is given by this one over here, and also we introduce something called a tensor. A tensor is, we can think of it like a bookkeeping element that insists that the way something transforms from one reference frame to the other, we insist it acts in a certain way so that we retain the laws of physics. So we're building towards this idea of general relativity that is, which is, as the name suggests, that it holds true in every single situation. And as you can see, if it holds true in every single situation, then we need an understanding of what the universe is like in every situation, which is why we was looking at the curvature of the universe. That's why the equivalence principle was needed as a bridging gap between the special and the general relativity. So now that we have an idea of what the universe looks like, we have an updated idea of what it is, that brings us to our Einstein equations. So basically, if we know what the universe looks like, we're going to be able to model and describe them using these equations. So these equations basically relate how the distribution of matter and energy in the universe affect the curvature. So and if you think about it, that is basically gravity, right? So we've solved the issue of special relativity of it not obtaining gravity. We derive these equations. By looking at we derive these equations by looking at what reduces to the Newtonian mechanics. So all these equations in the non-relativistic frame should reduce to simple Newtonian mechanics. So we worked backwards by looking at what reduces to what to be able to extrapolate that backwards to building these Einstein equations that model and govern the whole universe. There are different Einstein equations, but they're all variations of the same thing. So when we introduce the cosmological constant, which is this one over here, this is to account for the expansion or the contraction of the universe, and it's one of Einstein's greatest blunders, actually. Sorry, one point I forgot to add is that general relativity, the idea of it is that it's general, that it's all-encompassing, and these equations help us describe everything in the universe. So as we can see, special relativity, the equivalence principle, which leads into differential geometry, which leads into the Einstein, which leads to general relativity, which leads to the Einstein equations. Now, from the Einstein equations, we can actually take it one step further. It's like a river that flows into each other, right? And we can go to the Schwarzschild solution, which is actually just a solution to the Einstein equations. So imagine we have a differential equation, dx over dy, we are solving for y. So the Schwarzschild solution is the solution for y, you could think of it. Now with the Schwarzschild solution, we imagine a black hole which is non-rotating and static, and oh my god, keep going. You have access to the slide, so you can see how that there are no cross terms involved. The reason is because it's static, so we assume that the space-time doesn't change. We're able to make a guess solution, which is only, and because it's symmetrical, then it's we're able to work out the polar coordinates in a certain way, and we know that because it's symmetrical and non-rotating, we're able to make a guess. That guess leads us to a set of differential equations, which allows us to work out a metric, which is a description of space-time. A bit similar to the Einstein equation, but a little bit different. It's a description of space-time. So this black hole line metric, this black hole line element gives us a description of that singularity. And we can also now that was for a Schwarzschild black hole, one that is static and non-rotating. But obviously, like with all things, black holes come in different shapes and sizes, right? So we have what is called an anti-de Sitter black hole. And an anti-de Sitter black hole is something that it is a black hole that exists in a space-time whereby the curvature is such that it looks like the shape presented to you on the screen. It's a bit like a horse saddle. So we do the same thing. We go back to the Einstein equations and we solve them, except the Einstein equation has been tweaked a little bit this time. The Einstein equation will include a cosmological constant, and whereby in this case the constant is smaller than 0. So we factor that in, and that gives us a different line element to before, a different one for a black hole in anti-de Sitter space. There are also many different types of black holes. There is something called I can't pronounce it, but it's a charged black hole. It's a black hole with a charge, and it gives us, once again, it gives us a different metric than the anti-de Sitter black hole. There's also a Keir black hole, which is a rotating black hole. Okay, so the thermodynamics of black holes. So a lot of those ideas were from the mid 20th century, all the way to Newton. So, but this is pretty recent. This is Stephen Hawking. So the idea is the motivation for Hawking radiation was the idea that a black hole's surface area, it never decreases. And if two black holes were to merge together, the total surface area would be greater than the two black holes that merge together. Now, what does that sound like? That sounds a lot like entropy. We know that entropy can never decrease. We know that entropy can never decrease, so therefore we can interpret somehow the surface area of the event horizon of a black hole to be similar to entropy. If there's an associated entropy with a black hole, then we also know that there could be an associated temperature to the black hole, because entropy and temperature are related via thermodynamic laws. So that's the motivation for Hawking temperature. That's how this idea that a black hole could act like a emitting radiation body. That's how it occurred. We derived this formula over here from looking at the wave function, from performing a Wick rotation on a black hole metric, and from also deriving the derivative of the function from the black hole metric in a long derivation that produces the formula over here. So this is the temperature inversely proportional to the mass. And now here, and we can also see that we can do that for other different black holes. So that formula previously was for the Schwarzschild black hole, and that is this line over here. We can see how it is inversely proportional to its mass. We can see as as mass increases, temperature goes down, so inversely proportional. But when we look at the anti-de Sitter black hole, we see something very interesting. We see that for low masses, it follows the same idea as the Schwarzschild black hole, but then as mass increases, so too does temperature increase. So it's really strange. And then for the Reuchner, it's the black hole with a charge, we see this kind of like funny shape. It's a increasing function. It reaches a maximum point, and then it kind of like does a inversely proportional between temperature and mass. So it's really strange seeing how all these different black holes have different relationships between their Hawking temperature and their mass. It's not all the same. Now, I want to give a physical interpretation of Hawking radiation. Hawking radiation is something that, how do we understand that something is being emitted from somewhere whereby not even light can escape, because oh my god, because how can we imagine the idea of something escaping the universe's biggest escape jail, if you like, when even light cannot escape? How is a particle going to escape when light itself can't escape? So we kind of think of it this way. So we know something called quantum fluctuation. We know that quantum fields permeate all of space-time. And we know that from these fields, there can be fluctuations which are particle-antiparticle pairs. So they can appear out of nowhere. Well, they don't appear out of nowhere, they appear out of energy from that field. So inside of the event horizon, or on the event horizon rather, we can have a pair production of a particle-antiparticle pair. The idea is that when that happens, one of the particles actually shrinks back into the singularity, and it detracts from the mass of the singularity. We know this because energy is equals to mass. The other Einstein equation, mass is equals to the speed of light squared. Energy is equals to mc squared. mc squared. So it decreases from the singularity. And if the mass of the overall black hole, if the mass of the singularity increases, then the event horizon is going to shrink, because the black hole in itself is going to decrease. So this event horizon actually moves backwards. And if the particle is stationary, then it's going to appear that the that the particle has actually escaped the event horizon. It's going to appear that the particle is going to escape the event horizon. So that's actually how it happens. That is how the particle escapes. It is the shrinking of the black hole from this pair production that has just come out of nowhere. We have to rewrite the metric so that it's non-zero at the event horizon, and we also have this nice probability over here, which is the probability of this actually happening, and we do that by working out the momentum of the system. The same way we use that that gives us the probability of this happening, and this is actually a refinement on Hawking radiation. And just as a step further, we also have the information paradox, which is basically this idea that if black holes do emit radiation, then there's this chance that there's no resemblance between the particles that went in and the particles that went out. That means information is lost. Now, this idea of information being lost is not something scientists are happy with, because it breaks certain laws of physics. It's called the information paradox, and it's reconciled by this idea of super translational charges being conserved, which is basically as you zoom out of a black hole, space-time appears symmetrically flat. It allows for observed quantities of super translational charges, and scientists believe that this is where some of the information can be recovered. Thank you for watching.